In this part of the lecture, we will focus on how to correctly describe model parameters. This one is really critical step in the simulation, because even a well-designed model can produce misleading results if its parameters are defined incorrectly. So, constructing a conceptual model, we have defined what are the key elements of the system. In the same time, we did our first estimate what could be associated parameters with a specific element. Now it's time to understand the nature of each parameter. So it's not really from one side complicated task, because as you see we have only two options. So a specific parameter has a constant value, or we observe some randomness. And now the task is quite clear. We need to catch up what is the nature of a specific parameter. As example, a rival. In most cases, it's clear that a following process has a random nature. So meaning that we are not able to define some specific constant interval. Again, as example, vehicles arriving to a warehouse. A queue size, most probably it has a constant value. I'm talking here about the maximum possible queue size. A processing time. Seems that it can be random, meaning that we are not able to predict what would be the processing, or it's really very complicated to describe this one. And finally, number of processing units. So it could be a constant variable. Of course, to be a bit more closer to the reality, it's quite clear that the number of processing units could follow some specific schedule, could consider failures, but in overall, again, we are dealing with the constants. So, we have identified what is the nature of each parameter. So just to remind you, we did a simple exercise trying to find out if a specific parameter has a random nature or it's a constant fixed value. Now let's go deeper inside. Let's try to see how we are able to describe a parameters inside the model. Let's start with a simple thing, is a constant. So meaning that we have a fixed value. So like a number of processing units, a maximum queue capacity. In this case, we could describe this one in the model as a specific fixed value. So our type random, meaning that somehow we need to include randomness inside the model. And here, as you're able to recognize, we have three different approaches, I would call them, how to represent randomness inside the model. So the first one says defined by real data, or sometimes we refer like inclusion of traces. The second one is based on constructing empirical distribution, and finally, I would say the most useful is description of the randomness using theoretical distribution laws. So now let's try to explore each opportunity which we have just discussed, and I'm starting with the case 1. Just to remind you, in this case we are going to define the parameter using real data. So just try to see a very simple system which we have already discussed for several times. We have arrivals or flow as indicated here. We have queue. As a processing unit we have cache machine, and finally exit. I believe a workflow is pretty clear, and inside your head probably right now you are having the following picture. So what we did, somehow we are not discussing how it happened, but we have collected a small data set, so which consists from 30 cases, so 30 items. And as you see, we have collected the information about the processing time, meaning that for a first person, which we have observed, the processing time was 20 seconds. For the second person, it was 40 seconds, and so on and so on. So what actually means the approach which we are discussing? The approach means that we are taking the data set and we are integrating the following data inside our simulation model. So the following picture represents the simulation model. So what does it mean? It means that during the simulation for the first person, a processing time would be 20 seconds. For a second person, a processing time would be 40 seconds, and so on and so on. Where is the problem or an issue of such approach? I believe it is clear. Our data set is really very small. Maybe we have collected a following data set just, I don't know, we have spent 10 minutes to collect the following data set. And now let's imagine that we need to simulate the behavior of a following system for 1 hour or for few days. It means that in this case our data set is really limited to represent the behavior of the system for a significant amount of the time. That's why the following approach, to be honest, not really popular if we are talking about practical application of a simulation modeling. So let's consider the second approach, case number 2. In this case, the parameter is defined using an empirical distribution. Instead of using individual observations, we group the data into time intervals, as you're able to see, and for each interval we calculate how many cases fall inside the specific interval. So you could see it here. And what we are doing next, we are calculating the probability that observation would fit the specific interval. So the result of such simple manipulation is a discrete distribution that approximates the real behavior and can already be used directly in a simulation model. So to continue a discussion about the second approach, case number 2. Here we use the empirical distribution which we have just developed inside the model. So meaning that each processing time value is assigned considering the probability. The main advantage is that we can now generate realistic processing times for any number of the entities. While still we have an issue. What kind of issue? Or maybe not the issue, but we need to consider that in this case we are losing some precision because we are utilizing intervals average instead of a specific random value. So moving to the third case, first of all I would like to state that this one is the most powerful tool which we have to describe the randomness. As you're able to recognize here, we are trying to find out a theoretical distribution which describes the data set. So a following task is known as a distribution fitting. So what it allows us to indicate that a processing time is described with a specific distribution, and using a following distribution we are able to generate realistic random values. In the same time we are keeping the model simple and flexible. But this one we are going to explore during a model development phase.